Welcome everyone. The title of today's notes is Solving Exponential and Logarithmic Equations, and it sort of represents the last algebraic skill before we get back into the applications and modeling with exponential and logarithmic functions. So there's still some really good stuff that we're going to look at over the next few days, but in order to be successful with that, we kind of need to be able to solve some equations and work with some of the outputs and solving inputs and stuff like that. So I think we have the foundation to be quite successful with this, and so we're going to dive right in. And it looks like on your notes worksheet I wrote a few strategies down, and let's see if we want to highlight any of those. I'll just read them off and then we'll kind of come back to it. So strategy number 1, convert from one form to the other. And if you remember correctly, one of the things I said was the most important little skill of this entire unit is to be able to convert an equation from exponential form to logarithmic form, or to go from logarithmic form to exponential form. And so as a matter of fact, I think that's exactly what we're going to see right here. So put a big asterisk next to number 1 if you would. And then number 2, remember logarithmic properties from the previous notes worksheets. We can combine logarithms together via addition and subtraction. So we'll take a look at a couple of those. Those who have a TI-83, you're going to need to use that change of base formula to evaluate a logarithm. I think I had mentioned this on the previous notes worksheet. We're going to see logarithms in all types of bases, and the calculator should be able to get us whatever we need. And then number 4 is just check your answer. You'll see a couple of situations arise where it might look like we've solved correctly and everything looks good, but we've potentially changed the form of the equation. And if we change the form of the equation, we might not be able to account for some of the conditions. And specifically that occurs with logarithmic equations. And we'll see that in just a little bit, so we'll hold on to that idea. So I guess the best thing to do is to just kind of dive right in. I'll kind of show you how I solve some of these equations, and it sort of builds up in difficulty as we go through the process. There's really nothing like just getting some experience in practicing some of these. So that's what we'll do here together today. Alrighty, well it looks like I've got a set of logarithmic equations to start, and then some exponentials, and then just a few models to take a look at, and we'll solve accordingly. So here we go. Example 1. This reads log base 2 of 4 plus 3x equals 5. And if you notice, the variable here, what we're trying to solve for at this point in time, is sort of stuck as the input of the logarithm. And I can't really have that. I need to be able to free that up and isolate that and get it by itself to solve for it. So here's how we're going to play it out. As I had you right above, everyone see that 2 right there? Well, very simply, let's circle the 2. And let's roll it on over to the other side. And so we kind of talked about this before where, okay, logarithmic form doesn't allow us to solve for the variable, but by moving that 2 on over to the other side and bumping this up as 2 to the 5th, and I'm going to write that here as 2 to the 5th, well then it actually becomes pretty easy to solve from here because I've changed the form of the equation. If you sort of take a look at what we had a logarithmic equation, and again the variable was part of the input, but when I roll that over and treat it as an exponential equation, well then it actually just turns out to be linear. 4 plus 3x equals 32. And then, from here I think we can pull this off without too much difficulty. So let's bring the 4 on over, and let's divide by the 3, and 28/3 is definitely satisfactory here. If you plug that back in, it should read nicely there. I'm assuming you get a 32 in here when all's said and done. And log base 2 of 32 is definitely 5. Again, so it's that idea of convert from one form to the other. When you roll it over, you free up what was at that point in time sort of stuck, unable to really get by itself. Okay, so that's how we're going to play it out here. Example 2 is a little more difficult because what I have is really the sum of 2 logarithms, and so I need a way to account for that and then convert it over. So I hope you would all agree with me right away on this one, that there's nothing, I can't roll over the 4 just yet because I have 2 logarithms. So if you think back to yesterday's lesson with the properties, I can add 2 logarithms together. I can combine them together into one by multiplying the inputs, what's called the product property. So again, if you look above on some of the strategies there, it'll talk about those properties, and we'll see those across the board today. So let's see if we can maybe take care of two steps here. At this point in time, I've got log base 4 of the x times x minus 3 equals 1. And it looks like I'm going to want to go ahead and roll over the 4 at this point. And so everyone, if you want, circle the 4. At this stage, I'm not going to, but I'm just going to show you right here. That 4 is going to roll on over to the other side. And at the same point, let's clean this out just a little bit. It looks like I get x squared minus 3x, and then 4 to the first. And if everyone's okay, that's going to be 4, of course. I just wanted to highlight where that would come from. So that is 4 to the first right here. And remember now, in this particular case, look at what we've done. We've changed it really from a logarithmic equation to a quadratic equation. It's x squared minus 3x. I'm actually going to bring the 4 on over. And so it's x squared minus 3x minus 4, and that equals 0. And now if I asked you to solve this quadratic, well, this should be in our comfort zone. We can solve it any number of ways. I'm going to try to factor it and just to see if this works. And it looks like that should be it right there, x minus 4 and x plus 1. And that looks great because if I can factor it, then I can get my two solutions to that quadratic right here, which would be 4 and x equals also negative 1. Now, that looks absolutely outstanding. Here is the sole dilemma with this. If you look at those two answers, they definitely work for this quadratic. This one right here that I'm highlighting, they work perfectly. The problem is they don't necessarily work for the original equation. So think about it for just a moment. I would argue in this particular case, if we put one of those values back in for x, it's going to work. In fact, I can kind of visualize that, and I see that it is an answer to the original equation. The problem is one of the other ones, well, the other one I should say, if I put it back in, it simply doesn't work. And so think about which is which there, and then I'll highlight. I think this one, everybody, is what we want. I think 4 works in the equation. If you put it back in for x here, and if you put it back in for x here, it works perfectly. Here is the dilemma, of course, everybody. What happens when I try to put negative 1 back in as the input of the logarithm? Well, it makes this negative here, and also it makes this negative here. And can I ever take the logarithm of a negative number? No. Log base 4 of negative 1 simply doesn't make sense. So we get, and if you sort of look at number 4 there, check your answer, watch for extraneous solutions. If you remember extraneous solutions, they work in the modified equation, but they don't work in the original equation because the original equation has conditions that the modified doesn't. In this case, logarithmic equations have a condition. Can't have it, well, we can only have it be positive. Okay, so just be careful. It doesn't mean that x can't be negative. It means the input can't be negative. And so in this case, it makes the input negative, and so it doesn't work. All right, I hope that works for you. Please ask if something comes up and you're not sure about that. But 4 is the only one that works there. Okay, let's get into example 3. Just another logarithmic equation here. It looks like very similar. Instead of a plus in between, it's minus. So I hope everybody would be in agreement here that this is going to be the quotient property. And so it's x plus 2 over x minus 1, and then equals 1. So again, now you're seeing it 2 times over. In this particular case, what we want to do is combine the logarithms together first, then we can start thinking about the rollover. And you do know that 4 is moving to the other side. There's just no way around it. And because my variable is part of the input of a logarithm, in order to get it available to solve, we need to go ahead and change the form. So everyone, bring over the 4, roll it on over to the other side, and if I roll it on over, I get 4 to the first, which is just 4, if you're okay with me doing that at this point. Now in this case, it just seems like it's a rational equation. Let's see what happens. I think we should probably just cross multiply here. If you want to put this over 1, you're more than welcome to. But I see this as a 4x minus 4 equals x plus 2. And again, I'm just cross multiplying in that case. I'm going to bring over the x, so this is coming over to this side, and I do get 3x. I'm going to bring the 4 on over, and I do get 3x equals 6, and so x equals 2 as a result. Okay. Now again, we should put that back in just to see. So it doesn't matter if this is positive or negative. Let me be very clear on that. It doesn't matter what this is. It matters what it would make the input of the logarithm. And so when I put the 2 back in, log base 4 of 2 plus 2, that's fine, log base 4 of 4. And then over here, log base 4 of 2 minus 1, so log base 4 of 1. Those are things I can do. And as a matter of fact, if you do put the 2 back in and evaluate those logarithms, it does balance the equation there. You end up getting 1. So that one will keep. All right, so now we've done 2, kind of putting those together and then rolling it over accordingly. I think I'd mentioned we do a lot of work with exponential models in base E and also logarithmic models in base E. So here is a logarithmic equation, base E, and we're going to do a rollover in just a little bit on this. We might need the calculator to do a couple things. We'll see how it goes. But let's go ahead and talk about this piece. So I've got 4 times the natural logarithm of 3x minus 1 plus 6 equals 18. And I hope you realize at this point that I am not ready to roll over that base E. That's not in the cards just yet. What I probably want to do is isolate the logarithm first. So everybody, I'm going to subtract 6 on both sides. First order of business, let's just start undoing these operations here. And so you should get a 12 as a result. Second step, and there are actually a couple ways to do this. If you can think about this, I'm just sort of thinking out loud. We can apply a power property here if we really wanted to and kind of bring that up. I think that is probably the lengthier approach to this, to be honest. I would divide by 4 first and just get ln of 3x minus 1, and that would equal 3. So again, there are some options here. Working with properties of logarithms, but I don't think that's the way to go here. I think it's isolate the logarithm, and then let's roll it over. And that's what I have at this point. I have the natural logarithm of 3x minus 1, and that's equal to 3. And so remember that natural logarithm really just means log base e, and so I am going to roll this on over to the other side at this point. The e rolls over, and that allows the 3x minus 1 to come out, free as a bird. And I roll over the e, and I end up getting e to the 3rd here. Now, e is sort of, well, it's not sort of, it has the same properties as pi. And if you remember in your geometry class, sometimes you would represent your answers in exact form using pi. Sometimes you would approximate. I would argue for all the models that we're going to do, rather than keeping this as e to the 3rd, it's probably to our benefit to go ahead and just get a decimal approximation on it. So what I'm going to ask you to do is actually take the next couple steps there. I'm going to write my final answer momentarily. But basically what I'm going to ask you to do is grab the calculator and take e to the 3rd on the calculator, and then add the 1, of course, and then divide by the 3. So at this stage, it just becomes a linear model. This, remember, of course, is just a constant. You're going to get that from the calculator and then solve for the variable from there. And if you do, I believe you get something around this. So this is what I have on my paper. And again, if you, for some reason, don't pull that off, you'll just let me know about it. But again, I would argue that for all of our modeling, we're going to want the approximation. You know, rather than saying something along the lines of, oh, it's e to the 3rd plus 1 divided by 3 years until this happens. No, I mean, I think it's just a little better that, hey, it's about 7.029 years. So I think the approximation just has a little more meaning here. All right. So we've done 4 logarithmic equations at this point, and I hope they're looking pretty good. As you go through the process, just think about the rollover, think about the properties, and so forth. Let's get into the exponentials. So example 5 now. So again, a lot of modeling here. In this case, as you can see, we have the same dilemma. What I'm trying to solve for is stuck as the input to a power. It's the exponent in this case. It's tough to isolate it to get an x by itself when it is part of a larger expression. In this case, it's part of this power right here of base 6. So I need to find a way to free that up. And so here's how it's going to play out. First order of business, though, is to bring that 7 over to the other side. So let's do that. So I get 2088. And in this particular case, I have a nice exponential equation here, but it's actually not very user-friendly because, again, the variable is part of the power. But there's a way to kind of free that exponent on up and get it by itself, and that's by changing the form. And so one more time, everybody, here's the premise. Circle that 6. Remember, the base is what rolls over to the other side. So circle that 6, everybody, and roll it on over. And when it rolls on over, remember what happens. This is the key. It changes from the base of the power to the base of the logarithm. And so now if you look at the left-hand side, it's ready to go. Obviously, in just a moment, I'm going to add the 4 and then divide by 3, and I can get that variable by itself. It's ready. The right-hand side is what I have to deal with here, everyone. And we haven't really seen this before or been able to work with this, but now we are. What is log base 6 of 2088? Well, just conceptually, what I would be asking here, and again, I'm hoping you're on board with this number right here really means 6 raised to the what is 2088. Well, I don't know my powers of 6 that's going to get us there, and so I think we're going to have the calculator give us a hand on this, and that shouldn't be a problem. Again, if you have a TI-83, and I'll bring mine up momentarily, you're going to do the change of base formula. If I believe you have the 84 plus, you can do this without the change of base formula. See if you can find it, and if not, you'll ask. Remember, everyone, it's log of the input divided by log of the base. So I'm just going to write that off to the side there. That's what log base 6 of 2088 is. It's log of the input divided by log of the base. And so I'm going to bring this on up here and do exactly that, everyone. Log 2088 divided by log of 6, and press enter. And we're going to go to about 3 decimal places there. And so again, I ask myself, hey, 6 to the what equals 2088? Well, 6 raised to the, and it looks like 4.266. So let's put that in, 4.266. All right, now I hope that works for you, because now it becomes a fairly simplistic equation. So when you get an opportunity here, I'm going to ask you to run those last 2 steps. Everybody add 4 to both sides, please. Then divide by 3 on both sides. And I believe when you do that, you end up getting an answer of about 2.755. Again, if anything's off with that, you'll let me know. But that's how we're going to solve these exponential equations. Rolling it over and then using the change of base formula to evaluate the logarithm. Excellent. All right, hope that one worked. Let's do one in base E. Again, a lot of work in base E. And actually, there's some benefits to working in base E, because we're not going to need the change of base formula. When we roll over, it just changes to the natural logarithm, and so I think that's useful. Okay, again, just be careful. Before you decide on rolling that over, you've got to isolate the power. And so what I mean by that is let's divide by 7 first. So e to the 2x, 63 divided by 7 is definitely 9. Now, again, we're in a similar situation to the last one. This is what I'm going to roll on over to the other side, everybody. And as I said, it has to be automatic from here. The way I want us to look at it is it rolls on over, the 2x comes on down, and remember it changes from the base of a power to the base of a logarithm. So it's log base e, which is really the natural logarithm of 9. And this is great because, as I said, there's no need for a change of base formula here. This is on your calculator. This is primarily stored. And so what you need to do is just hit the ln button and 9. So take the natural logarithm of 9. That's some decimal, of course, and then divide by 2. Again, if you have any issues with these last steps that I'm sort of glossing over, please at any time let me know. And we can definitely walk through it hand in hand. But basically, should be able to calculate this and then divide by the 2. And I end up getting about 1.099, so you can see if you did that correctly there. All right, that's great. Again, nice working in base E. It's quick and simplistic because of that piece right there. We don't have to do a change of base formula on it. Okay, we've done 6 at this point in time. We're going to keep it moving. We'll see how many we want to do here and see how the timing works. Example 7 is sort of a culminating piece with exponential equations, and then it looks like we'll try just a few models if we get an opportunity. So last one here, and you see a couple dilemmas arise. If I look at the left-hand side of this equation, I have the variable as part of the exponent, so that's not good. It's attached as a component of that power. But then I look to the right side and I have that same variable, and now it's attached to a different power. So I have a lot of issues here. There are a couple ways to solve this, by the way, if you happen to do a little research on this and you find a different approach and that one maybe works for you a little better, that's fine. It's really the same thing, just a slightly different look at it. But I guess I would go ahead through this with the same philosophy, the same mindset. And so what I'm going to do is a rollover. So everybody, it doesn't matter which side. We've been kind of going left to right there, just the way these have been working out. So everybody, I'd encourage you to circle the 5, as I'm doing here, and let's roll it on over to the other side. And watch what happens here. This is a good one, so really be on track with this. But that rolls over, the 2x plus 1 comes down, which is what we wanted. Remember what happens, everyone. As that 5 crosses the equal sign there, it changes from the base of a power to the base of the logarithm. So it becomes log base 5 of 6 raised to the x minus 2. Now here's what I'm wondering. I'm curious if you happen to see something intriguing on the right-hand side, specifically with the input of the logarithm, the 6 raised to the x minus 2. Does it look like we can do something with that to kind of clean up the fact that that x minus 2 is the exponent of that input? Yeah. And think back to yesterday. Look at think about it as the power property for logarithms. Can that x minus 2, can that go out in front right here of the logarithm? And that's exactly what that power property had stated if you kind of look back on that piece. So this x minus 2 becomes the factor in front of the logarithm. And that becomes x minus 2 times log base 5 of 6. Now, it's going to get a little ugly here just because of the bases that we were looking at, the 5 and the 6, because I do have log base 5 of 6 here. And so again, remember what this number means. This is a constant, everybody. And this is basically saying 5 raised to the what would equal 6. That answer is definitely the value of this logarithm right here. And again, I'm just going to write it off to the side. If you don't need to, then don't bother. But basically, that is log of 6 divided by log of 5 if you're going to use the change of base formula. So grab a calculator, please. I'll do mine as well. And let's go ahead and just take a look. So this would be log of 6, and then divided by log of 5. And so we get about 1.113. So let's be very clear about this piece. When that x minus 2 came out, then we just get a nice logarithm right here, numerically, is 1.113. So I get a 2x plus 1 equals x minus 2 times 1.113. Excellent. Now, everyone, it's just time to distribute here. And let's go ahead and solve. I think we can pull this off. 1.113x minus 2.226. And again, now it's just a linear equation that we can solve for. I would bring this term on over to this side right here. I would bring the 1 on over to that side. And if you do that, if you bring this over here, I believe you get 0.887x. And then if you bring the 1 on over to the other side there, you end up getting about negative 3.226. Sounds good. I'm going to go ahead and divide just one more step here to solve for the variable, and should get about negative 3.638, somewhere in that vicinity. That's what I have on my paper there, and take a look at that if you get an opportunity. All right, so solving an equation there with 2 powers, one equal to the other, variable in both of the exponents. Take a look at that piece, and I hope everything kind of works well with you. We did a rollover, which is kind of the way we've been doing all these. Then that power property, that's the key right there. That power property makes that x minus 2 come out in front. Okay, so take a look at that piece if you get a chance, and please ask questions on it. Let's do a couple more here, and again, we'll just kind of see what the timing is. Hopefully you're getting some good practice on it, and it's starting to really click for you. Should be able to have any exponential or logarithmic equation at this point and kind of work through that accordingly. All right, let's go for it. Example 8. $1,000 is invested into an account paying 7% compounded monthly? How long until it reaches 2,500? And what if it's compounded continuously? So it looks like we're going to do 2 of these. And just to start getting back into this a little bit, the hope is you know your compound interest formulas. That would be for anything except continuously. And of course, the PERT formula would be for continuously. All right, so we're going to just plug in all the information that we know here. We're going to kind of do it side by side and solve accordingly. So it looks like we start with $1,000. That's our principal. I have 1 plus 0.07 for our rate. Monthly means 12. We get 12 interest payments per year for a certain number of years, and we want to know how many years until that $1,000 reaches 2,500. So everyone take a look at that piece. We've seen this in action before, and really up until this time what we've been doing is solving it on the graphing calculator. That's actually the only way we've been able to do it. We've been plugging the right-hand side into the graphing calculator, plugging the left-hand side in the graphing calculator, trying to find a point of intersection. I would argue solving it algebraically is actually probably even more efficient, and I think it's quicker. So let's do it that way. Now we have the tools to pull this off, and so we're going to solve for t. And again, you notice the dilemma. T is part of the exponent there. So let's find a way to free that up and get it by itself. Well, again, everyone, we have to isolate a power here. So if you don't mind, I'm going to try to do 2 steps at once. I'm going to bring the 1,000 on over with division. I'm also going to look at this number inside the parentheses, and because those are operations I can do, I'm going to figure out what 1 plus 0.07 over 12 actually is. And so this is what I'm thinking occurs when I do both those things. First of all, the 1,000 comes over and I get 2.5. This number right here, and again, I would encourage you to go to several decimal places as a result, I get something like this. So please check this on your calculator. But if you do 1 plus 0.07 over 12, you should get that as the base of this power. And then this would be raised to the 12t. Okay, this is great. So now, again, just by doing those 2 things, excuse me, this is a more manageable equation. And so what I'm going to do at this stage, everybody, is I'm going to treat it exactly like those previous exponential equations. This one here, everybody, I'm going to roll on over to the other side. So that's the base of the power. It's going to roll to the other side. It's going to get a little crazy here, but that's all right. Log base 1.00583 of 2.5. That's equal to 12t. So again, that rolls on over to the other side, and it becomes the base of the logarithm. I told you we were going to see bases that were going to be a little strange, but that's okay. We're going to let the calculator do the work here. So let's see if you can do one pretty much on your own. What I need you to do here, everybody, is evaluate this logarithm on the calculator. And remember, it's not a big deal. If you're doing the change of base formula, it's log of the input divided by log of the base. So this would look like log of 2.5 divided by log of 1.00583. And if you do that, you should get something like this, about 157.545, somewhere in there. That's what I have on my paper. I hope that's legitimate for you. And then that equals 12t. Remember, t is always in years. And so we want to solve for that variable here, solve for the number of years, and we would divide by t at this point in time. I'm sorry, divide by 12 at this point in time. And when you do this, should get about 13.13 years. Okay, so notice the good things we did here. We definitely found the base of this the base of this power right here, and then when we rolled it on over, it became the base of that logarithm. And again, guys, need to be able to solve to evaluate any logarithm out there using the change of base formula or using the nice function on the TI-84 plus. Okay, so if it's compounded monthly, it'll take 13.13 years to go from 1,000 to 2,500. What if it's compounded continuously? So let's take a look at this and think about this for a moment as I'm writing this in place. So 1,000 getting up to 2,500, e raised to the 0.07 times t. That's the nice thing about this particular formula. It's a little more straightforward, a little more concise. But again, this is only for continuously. And remember the context for continuous. So think about this. We want to know how long it's going to take, in this case, for $1,000 to get up to 2,500. Well, here's what's kind of interesting about this piece. If it's being compounded continuously compared to being compounded monthly, do you think it's going to reach this value before our answer from part A or after our answer for part A? Do you think it's going to reach 2,500 before 13.13 years or after 13.13 years? Well, the argument, I guess, can be made that the more it's compounded, the more interest has a chance to earn interest over the time frame, and so the quicker it should probably reach this value here. Now again, is it going to be dramatically quicker? Probably not. Again, the more things get compounded, the more it levels off, even though it's increasing, and then the limit of how fast it can go is based on this compounded continuously. Remember what that means. That would be the number of compounding periods approaching infinity. So anyway, let's go ahead and solve. I'll bet you it's pretty close to 13.13 years. So same idea. Again, you can see working with base E, it's nice and concise. I'm going to go ahead and take that E. Again, you should be able to kind of pull this off at this point as well. Let's roll that on over to the other side. And when I roll that on over to the other side, I get the natural log of 2.5. Again, base E has some benefits to it. You don't have to worry about a change of base formula. Natural log of 2.5 is stored on your calculator there. So let's get that. And let's see if I have that. I'm just curious if I do. Actually, I do not. So I'm going to ask you to take these steps right here. Let's do ln of 2.5. And then I hope everybody would be in agreement that we would divide by 0.07. If you want, actually, I'll do this as well. So we would do natural log 2.5. And you get this right here, about 0.916. And then divide by 0.07. So, oops. Let me make sure I've got the right one. There we go. And so then divide 0.07. Yep. Let's do that one more time. ln 2.5. There it is, much better. Sorry, I think I slowed you down there a little bit. And you can see you get about 13.09 years. So did it reach a little faster? Yeah, it sure did. But again, only a touch faster. The more it's compounded, the more interest gets to earn interest, so the quicker it would reach the goal, so to speak. But the more it's compounded, really it doesn't have as much of a dramatic impact. What would have a dramatic impact on this problem is not how it's compounded, although it does, but the interest rate. As the interest rate goes up, you would reach the goal quicker and quicker and quicker. Okay, very good. You know what, I think what we'll do is actually skip 9. Just kind of looking at the time there, and this is one we just did a model in base E. You're more than welcome to kind of look at that piece. In fact, I'll just write an answer here. You end up getting about 0.0816. That's what I get. This is a blood alcohol content concentration, excuse me. So again, you can kind of take a look at that at your convenience. At this stage, I'm not seeing that as a necessity. This is sort of an interesting one. I kind of like this piece. So we'll end on this one right up here. So it says the function p of x equals 95 minus 30 log base 2 of x models the percentage of students who could recall the important features of a classroom lecture as a function of time. X represents the number of days that have elapsed since the lecture was given. So it says after how many days do only half the students recall important features of the classroom lecture? And by the way, this P is as a percentage, and I know we've been changing percentages to decimal. It just so happens this is a very specific model, and as a percentage, when it says after how many days do only half, and here's going to be the key, that would be 50%. Again, this just, I know the way the model works here, and that means we do put 50 in for the percentage, and we want to see how many days it would take. Oops, this is 30. Sorry about that. So 30 log base 2 of x. And so we're going to go ahead and solve this right here. A nice logarithmic equation, basically, given the output, should be able to find the input now. That's the stage we're at. So everyone bring the 95 on over. 50 minus 95 should be negative 45. There's my negative 30, log base 2 of x. So remember, before you think about any type of rollover, you either have to isolate the power or isolate the logarithm. And here, guys, I'm isolating the logarithm. I'm going to divide by negative 30. And by the way, negative 45 divided by negative 30 should be 1.5, and then log base 2 of x. Now I would ask you the question, are we ready to roll that 2 on over to the other side? And the answer is definitely yes. The logarithm is isolated. The variable is part of the input. In order to free that up, everybody, that 2 needs to roll on over to the other side. And when it does, it bumps up to 1.5. I hope everybody is able to just really do that automatically. And that should be our answer. If you do 2 raised to the 1.5 on your paper, or on your calculator, excuse me, I believe you get about 2.82 days, somewhere in there. So after just under 3 days, half of you will forget all the important good stuff that we did during this lecture. That's pretty depressing. Okay, now how about letter B? After how many days have all the students forgotten the important features of the classroom lecture? So this is a memory model basically, and if everybody's forgotten, 0% have remembered the important feature. So it would be 0 equals, I did it again, 30 instead of 3. So log base 2 of x. Hey everyone, I think I'm going to ask you to do this one. So I'm going to ask you to pause the video there, bring that 95 on over, divide by the negative 30, and do what you're supposed to do to free up that variable as the input of the logarithm, and solve. Pause the video, please, and then I'll write the answer up. Okay, let's see how you did. If you solved correctly for the variable here, I believe you get just under 9 days. That's what I end up getting. So take a look at that piece, see if that works for you. All right, so solving a bunch of equations. We're going to get back into modeling pretty soon, developing the model, then using the model. And we're going to do it all algebraically there. So I think we now have all the skills intact to pull that off. Please get the practice on this piece and let me know if you have any questions. And of course, as always, thank you for listening to the lecture.